the form of the solution to the ODE when we have a damped system is going to depend on the type of damped system we have. Is it underdamped, critically damped, or overdamped? However, the base solution is always going to be coming from the same place, solving that second order ordinary differential equation. So we're going to go through the different types of damping we could have and see what the form of the solution looks like. And we'll start with the most common system we're going to be seeing, underdamped systems. Again, the case where zeta is less than 1, and we're going to see that our roots of our characteristic equation are complex with non-zero real part and non-zero imaginary part. We'll look at the solution and then we'll derive it from solving the ordinary differential equation in general. So when we have an underdamped system with free vibrations, and we'll see this again for forced vibrations because this will still be the homogeneous solution to these types of problems, this is what the form of our solution is going to look like. We have some coefficient x, we'll have an exponential, and they'll be multiplied by a cosine function with a phase. Now, there'll be some simplifications that we can write. We have this omega n times the square root of 1 minus zeta squared involved. And we know from system dynamics that that is just what we call the damped frequency. And that's actually the frequency of oscillation that our underdamped system is going to have. And we can see that the period, or the damped period, will be 2 pi over that omega d. This is the type of system that we really focused on in system dynamics, were these underdamped systems. And remember that underdamped systems will have oscillations around the mean. And if we see the form that we have here, we have this exponential that's going to be e to the negative zeta omega nt. Well, zeta has to be positive, or we're only looking at stable systems where zetas will be positive. The natural frequency must be positive because it's the positive square root of k over m, and those are both positive. And t starts at 0 and only gets larger. So we have an exponential raised, or an e raised to a negative power. So what happens as t gets large is this term is going to start to get smaller and smaller and trend towards 0. The cosine term is going to be periodic. It's just going to oscillate between positive 1 and negative 1. So as time goes forward, we're going to have oscillations from the trig term, and it's going to decay. It's going to get closer and closer to 0 because of this exponential term getting smaller and smaller. And then the ultimate amplitude of this is going to be governed by this x. So more simply, we can rewrite this instead of having all this inside the cosine. We can simplify that to, again, just that damped frequency, and that's the frequency that this will oscillate. Now, we do have two constant terms here that we need to solve for. This is the general solution. We need to apply our initial conditions that we were given so that we can find these two constants, the amplitude x and the phase phi. And this is what we get for the amplitude and the phase. So if we compare this to the undamped system, the amplitude and the phase are a little bit more complicated to get to, but we'll be able to derive these from solving the ordinary differential equation and going through the steps like we did when we were dealing with the undamped system. Now we can go through the steps of actually deriving this equation. So we'll start at the point where we have the roots of our characteristic equation. We know that we have a second order system, so we know the general solution this is going to take. So these are the roots when we have an underdamped system. And we have, they're complex, so we can write in the form of a plus or minus j times b. So I can write this in general and then put in the specifics. So in this case, our a is this negative zeta omega n, and the b is going to be omega d. So just like we saw before, the general solution looks like this for our x of t. We're going to have some constant c1 times e to the at power times a cosine bt plus another coefficient c2 e to the at sine of bt. Now, when we were looking before at our undamped system, in that case, the real part of this a was 0 because zeta was 0. So what did that do? That got rid of these exponential terms, and we just had a cosine and a sine term. That's not going to be the case here, though. What I can actually do is factor out this e to the at power, and I'll be left with a c1 cosine bt plus a c2 sine bt. And now I can put in some specifics. So I know my value of a, this is e to the negative zeta omega n, c1 cosine omega dt plus c2 sine omega d times t. Now I can rearrange this a little bit like I did for the undamped systems. Instead of having a cosine term and a sine term, I am going to combine them into one term, one cosine term with a phase. So I'm going to have one amplitude, unknown amplitude, instead of a C1 and a C2. I'll just call that X instead. And I'll have a cosine of omega d t minus some phase value phi. And one last time of rearranging this so it looks like what we had on the slide, I can bring the X out in front, e to the zeta omega n cosine omega dt minus phi. So now we have the general solution that looks just like what we had on the slide. So our next task is solving for x and phi by using our initial values, our initial conditions. Right, so we're having this generic form, x of 0 is x naught, x dot of 0 is x naught dot. Again, what are we trying to do? We're trying to solve this one time here so that any time we encounter an underdamped system that's second order, we know what the general solution is going to look like as long as we know what our natural frequency is, the zeta is, and our initial conditions are. We're going to be able to just pop those right in and get our solution pretty quickly. All right, so again, this is our x of t. So let's see what x of 0 looks like. And there should be a t here that I was forgetting before. Okay, so I can put in 0 for t and see what I get out. So x is not affected by that. That's just x. I have e to the 0 because that t is 0. E to the 0 is just 1. So I don't need to write that. Cosine of, here I have 0 minus phi. So that's just going to be the cosine of negative phi. Right, now I'll put that aside for the moment. I'll call this equation 1 because I'll come back to it. Let's see in general what x dot of t is if I know what that general solution looks like. So I have to take the time differential of my x of t. I have a t function times another t function, so I am going to have to use the product rule in order to do this. So I'm going to have to take the derivative of the first term times the second, plus the derivative of the second term times the first to get my x dot of t. All right, so the x will come along for the ride. I need to differentiate e to the negative zeta omega n times t with respect to t. So the exponent is, or the coefficient in front of t in the exponent is going to come out in front. So I'll drop down this negative zeta omega n, and then the derivative of e is just e to that same power up top. And then that second term just comes along with us. Right? Plus, now the other part of the product rule, I have to differentiate the second term times the first term. So I need to differentiate cosine omega dt. So that's going to involve chain rule. I'm going to have an omega d coming out in front. And the time derivative of cosine, or the derivative of cosine, is negative sine. So I have a negative from cosine going to sine. I have an omega d in front because of the chain rule. Now I'm going to copy, I have an x e to the negative zeta omega nt, and now sine omega dt minus phi. And I can clean this up a little bit more. I'm going to have, I have negative signs, I have x, I have an exponential, so I can pull some of that stuff out. So I'll pull out a negative x e to the negative zeta omega n times t, multiplied by, I'm going to be left with here a zeta omega n cosine omega dt minus phi, plus I have an omega d, the x came outside, the exponent, the e came outside, sine of omega dt minus phi. And just a little bit cleaned up, factoring out some common factors. Now I can apply that second initial condition. So x dot of 0, I know, is going to be, I'll put this back up here too, x 0. So I can put in 0 for t. So I have a negative x out in front. E to the negative 0 is just going to be 1. And on the inside, I am going to have here zeta omega n cosine of 0 minus phi is going to be cosine of negative phi plus omega d, and sine of 0 minus phi, sine of negative phi. And again, I know that that's going to be some constant value x naught dot. All right, so I can find at least the phi value I'll do here. In a similar manner to what I did for the undamped system, I can take equation 2 and divide by equation 1. So negative x, zeta omega n, cosine negative phi, d sine and divide by my equation 1. I have x cosine negative phi, and then the denominator here, x naught. Some more simplifications. I have an x and an x that can go away. And now I can split up my numerator. So I'll write this as negative zeta omega n cosine of negative phi over cosine negative phi. And I'll distribute that negative inside, so minus omega d sine of negative phi over cosine of negative phi. And the right-hand side right now is the same. I have a cosine negative phi over a cosine negative phi. That's going to go just to 1, so I'm left here with a negative zeta omega n minus omega d. I have a sine negative phi over a cosine negative phi. That's the same as tangent of negative phi. Okay, and now let's take this tangent negative phi. I'm going to add that zeta omega n to both sides. So on my right-hand side, will have this x naught dot plus zeta omega n x naught over x naught. And I'm almost there. I know that tangent of negative phi is the same as negative tangent of phi. So this negative and this negative are going to cancel, and I can divide through by omega d while I'm here as well. So divide both sides, omega d x naught. All right, now I can take the arc tangent of both sides, and I'll do this in a 4-quadrant way, just like I did before. And I'll be left with our solution for that phase phi. And we get exactly what was on the slide. That is our phase, and it's going to be dependent on our initial conditions, our damping ratio, our damped frequency, the natural frequency, although the damped frequency is entirely dependent on the damping ratio and the natural frequency anyway. I won't here derive the expression for x, but it's going to follow much the same method that we used for the undamped systems, but it's going to just go through a lot of algebra. But it's coming from the same method, and that's how we get that amplitude x for these systems. So to recap our underdamped systems, this x of t is going to be our general solution, and we're able to find the unknown coefficients by looking at our particular problem, finding the initial conditions, and finding those system parameters, and we have our closed form solution for every free vibrating system that is underdamped.